All right, we're going to talk about exponential functions for 5.1. So we'll recognize and evaluate some of them with a base. Could be a whole number. It could be any number bigger than 0 for the base. We're going to graph exponential functions, use the one-to-one property. We'll recognize, evaluate, and graph exponential functions with the natural base e. And we'll use exponential functions to model and solve some real-world problems. Okay. All right, so here is an exponential function, f of x equals a to the x, where a is bigger than 0, like I said. It has to be a positive number. When it turns out, we'll talk about this later, but when a is between 0 and 1, it's exponential decay, and when it's bigger than 1, it's exponential growth. But here's some examples. Here's exponential growth, and here's decay. Actually, I'm sorry, this is decay as well. But we're going to actually just start with evaluating. So we're going to plug in negative 3.1 in for x, and we'll actually get a number. So for the first three, you can use your calculator. Just go ahead and plug it in. It would be 2 to the negative 3.1, which gives you about 0.116. So this would be, I could say, if I want to use right notation, I could say f of negative 3.1 ends up giving you 0.117 about. Okay. And then for the next one, 2 to the negative x, it's pi, so 2 to the negative pi. Just go ahead and plug it in. 2 to the negative pi gives you 0.113. So f of pi, in this case, gives you 0.113. Close to actually negative 3.1, which makes sense because this is 3.14, so it's 2 to the negative 3.14, and this is 2 to the negative 3.1. That's close. But the next one is f of 3/2 for this function. We're plugging in 3/2 in for x, so we have 0.6 to the 3/2. We can do that in our calculator. 0.6 to the 3/2. You can enter in a fraction if you have the new software, or just enter in 1.5, or use parentheses. 0.465. Okay. All right. Next, let's sketch a graph of some of these functions. Exponential functions, when the base, which we're going to learn, is this one right here. When it's bigger than 1, it's exponential growth, and it always goes to the point 0.1. So this is the point 0.1, and it's exponential growth. Okay. Now you can always graph that in your calculator as well. The only difference between g of x now is it's going to go a little steeper. It's got a bigger growth factor. Obviously, you can just plug these in your calculator. 2 to the x. And do a zoom standard window, and you'll see that it goes through 0.1 right here, and then it grows exponentially. We can talk about then the domain, range, y-intercept, increasing, all this behavior from this function right here. This one right here is y equals a to the negative x, so it's exponential decay. It always goes through 0.1. The domain is going to be negative infinity to infinity, all real numbers. The range is 0 to positive infinity, right? So 0 to positive infinity. The y-intercept is 1, or 0. I'll put it as an order pair, 0, 1. It's decreasing as time goes on. And the x-axis is the horizontal asymptote, and it is continuous. Okay. All right, next let's talk about E. E is Euler's number, named after Leonard Euler. It's spelled E-U-L-E-R. But E is the number he found that it's an irrational number like pi, and it comes from this. It comes from this right here. If you have the expression 1 plus 1 over n to the nth power, the limit of that expression as n approaches infinity. So as n gets really, really big, this thing basically goes to this. It does go to this number e. The bigger n gets, the closer it gets to this irrational number. Okay, that might not mean a lot to you right now, but you'll see our finance equation is this: a equals p times 1 plus r over n to the nt. You can see that that is embedded, this expression right here is embedded in this formula. So the number of times, as we calculate payments more and more with finance, that's n. So basically, as we calculate things more, interest more times per year, this approaches e, and we end up with this formula: p equals e to the rt. So let me show you those formulas. So here's the formulas then. This is our, for n compoundings per year, this is our interest formula that we'll use, our finance formula, and this is what's going to happen. We're going to use this if we calculate n times, or I'm sorry, continuously. Okay, those will be on your formula sheet. Let's try an example problem. Okay, so we have $12,000. That's our P. So P equals 12,000. Our rate is 9%, so I'll call that 0.09. And the balance after 5 years, so our time that we're going to leave it in for is 5 years. Now I'm going to plug that into the first equation, because when we compound quarterly, this is the equation we'll use. Alright, in which case we'll make that 12,000 is P. Just substitute in 1 plus the 0.09 over 4 calculations a year is quarterly. And then 4 times 5 up in the new, exponent spot. So this is how you would evaluate that. You can do that in your calculator. Another way to do it is to plug in this information via this app. So you go to app and you click on finance and do the TVM solver. Now n is the number of calculations, so here. So actually the total number of calculations is 20, 4 times 5. 4 calculations per year times 5 years ends up giving you 20 total calculations. Okay. The interest rate in this case is 9. You enter it in as a whole number, 9%. The principal value start with is 12,000. We're not going to make a payment. We're going to compound this 4 times a year. Calculate it 4 times a year. Hit alpha solve on the y equals, and it tells you we make 18,726. 18,726.11. That's the amount of money that we'll have after we invest $12,000. So you can do this by hand with the calculator, or you can use this app. Either way, you end up with your answer of 18,726. Now, if you're going to do it monthly, what changes is this changes to a 12, this changes to a 12, and if you go back to the calculator, then you change your total number of calculations to 60. 12 times 5. Okay, interest rate stays the same, principal value stays the same. Now we're going to calculate these 12 times a year. And if you hit alpha solve on that, that gives you 18,788.17. So that's your answer for monthly. And then continuously, we're going to have to use the formula APERT. All right. The principal is start with 12,000. E to the 9%, we're going to have to enter that in as 0.09 for this formula. Times the time, which is 5 years. And if you do that, you get 12 times E to the 0.09 times 5. Gives you, well, I meant to hit 12,000, so let's move the decimal place over 3. 18,819. 0.75 approximately. I entered it in 12 instead of 12,000, but you get the point. You can see that the more times you compound the interest, the more money you end up making it if it's an investment, or spending it if it's something that depreciates. Okay, so those are the two formulas we're going to be using. Pretty straightforward, really. Hopefully we can make a homework out video that will help as well.